Yeah, welcome all. So today we will be solving a very interesting problem from TIFR. So as you can see that the problem is given in such a way that it looks really difficult. So it's a true-false question. All right. So it's a true-false question. So you need to understand that x has to be necessarily finite. Will this be a true or false statement? So first, let us go through this in two separate. We will try to tackle this problem from with two distinct observations. Okay. So the first thing that we have been doing for quite some time is now see it's written that each continuous function is bounded from x to R2, right? So what is that continuous function that pops into your mind whenever you think about a continuous function? There are two functions, right? One is the constant function, it's always, and another one is the identity function. So here, as you can see, that from x to R2, it is given that the identity function is bounded. So it is given that every continuous function f from x to R2 is bounded. So this is given. Okay. So that means what? That means the identity function from x to R2 will always be bounded. All right. So what happens when you have the identity function a bounded function? So the moment you have the identity function a bounded function, this actually implies that x subset of q2 subset of R2 is a bounded subset or a bounded set. Okay, because if x was not bounded, then the identity function would have shot to either, it would have been unbounded. It's pretty clear, right? So the first thing that you need to understand is that since all continuous functions are bounded, the identity function will be bounded. So this is the first observation. So from this observation one, we get x is bounded. All right. Now, this is a proposition. So the proposition tells you that in a metric space, if all the continuous functions are bounded, then that has to be compact. Okay, but we will actually observe this in two ways. So this is observation one. So now one of the remarks, or let's say recalling property, that you need to do here is that the metric is always a continuous function. So the metric means the D. So suppose if you have x comma D a matrix D, so the map from x cross x to R positive union 0, so that means non-negative real numbers. So this D is always a continuous function. So now our goal is to prove that proposition is that will x be compact. So now since x is bounded and x is a subset of an Euclidean space, to prove that it is compact, it is necessary and sufficient to prove that it is closed, right? So now we need to show will this be closed. All right. So what we have in mind is that suppose it's not. So let x be a non-closed set. So the moment x is a non-closed set, that means what? There exists a limit point of x, let's say x naught, that does not belong to x. That is why it's non-closed, right? So because if it were closed, then all the limit points would have been inside the set. So since it is non-closed, x naught, there exists a limit point of x that is not in x. So what we will do is we will take x belongs to x, and we will take the distance function x comma x naught. So as you can see that since x naught is not in x, this is never 0, but also since it is a limit point, this will tend to 0 if I go outside x. So it's, I mean, at some point it is actually tending to 0, right? So now let us define this function. So f from x to R2, x goes to 1 by d x comma x naught comma 0. So let this be the function. So now why is this continuous? Because it is component wise continuous. The first component of this function is continuous, the second component of the function is 0, hence it is continuous. So both of these components of the function are continuous. But since x naught is a limit point, this is unbounded. Okay, so one component is always unbounded. Okay, because this tends to 0 as x tends to x naught kind of way. All right, since it's a limit point, that means what? Every epsilon, every deleted epsilon neighborhood of x naught contains infinitely many x, since this is a limit point. So that is the reason 1 by 1 mod dx comma x naught will always be unbounded. Okay, hence what we prove from here, hence x is closed. All right, so the fact is that now x is closed. So from observation 1, x is bounded as well. So what does that mean? If I just add closed and boundedness, it means x subset of q2 is compact. Okay, so that means what? That means if you do not even take a finite compact set, and we all know that over a compact set every continuous function is always bounded, right? So you can think of it from this way as well. So to make it a false statement, what you can also do here is to understand it like this way, that take any compact subset of R2 that is sitting inside Q2. So then each continuous function has to be bounded, but then x need not be necessarily finite, okay, because it can hold, it is holding for any compact subset. Hence this statement is false. So the solution that we have done here is the proof of that statement is that this is an if and only if statement. Always remember it, that if in a space and it is a metric space, so let's say x comma d metric space, then all the continuous functions are bounded if and only if x is compact. Okay, so if x is compact, then of course all the continuous functions are bounded. So now what we proved here is the other way around, like when every continuous function is bounded, then we proved that x is and in this setup x is both bounded and closed. Okay, all right, so that's it for today. Thank you for joining. We will meet with another problem in the upcoming class. Thank you.